So, have you ever really stopped to wonder why your phone, your laptop, everything has a dual-core or a quad-core processor? I mean, why did we stop trying to make one computer brain that was just insanely fast and instead start giving them multiple brains? The answer, it turns out, isn't just some boring technical detail. It's a fantastic story about technology hitting a massive wall and then having to find a completely new, revolutionary way forward.
And for decades, this was literally the reality. Programmers had this thing they called the free lunch. They didn't have to get all clever and rethink their software to make it faster. Nope, they could just kick back and count on the hardware engineers to cook up a speedier chip next year. Performance improvement, it was predictable, it was automatic, and honestly, it was a pretty sweet deal for everybody involved.
And we're not just talking about tiny incremental improvements here. From the 1980s all the way up to the early 2000s, computing power was in this absolute golden age of exponential growth. Every single year, computers got noticeably, dramatically faster. It felt less like engineering and more like an unstoppable force of nature.
I mean, just look at this timeline. It shows that incredible acceleration. Engineers were pulling out all the stops, using tricks like pipelining, which is basically an assembly line for computer code, and something called instruction-level parallelism, or ILP. Now, this ILP thing is really clever. Imagine one master chef who's so fast they can start chopping vegetables for one dish while a sauce is simmering for another. They're doing multiple tiny steps of the same overall recipe at the same time. That's what processors did. They'd find these tiny, independent tasks within a single program and just juggle them all at once to create this illusion of incredible speed.
It seriously seemed like this party was never going to end. The improvements were so consistent, so reliable, that the entire tech industry was basically built on this one single assumption. Computers will always get faster. But this unstoppable force? Well, it was about to meet a truly immovable object.
So around 2004, the free lunch was officially over. The music stopped. And the problem wasn't a lack of brilliant ideas or some failure of engineering. The problem was way more fundamental than that. It was just a law of physics.
Okay, so here's the crucial point. As you make a processor faster, it eats up more power, and all that power gets turned into heat. We finally reached a point where the chips were getting so dense and so fast that they were generating heat faster than we could possibly pull it away. Making them even a little bit faster would make them so hot they would literally start to destroy themselves. This was the power wall, and it changed the entire game overnight.
And this right here shows you the immediate fallout. The responsibility for making your apps run faster suddenly shifted. The burden was tossed over the fence from the hardware engineers to the software developers. From now on, if you wanted your program to run faster on the latest machine, you, the programmer, had to figure out how to write it in a totally different way.
So, what was the answer? Well, it was actually pretty elegant when you think about it. If you can't build one single engine that spins twice as fast without melting, why not just build a machine with 2 or 4 or 8 engines, all running at that original, cooler speed? This was the brilliant strategic pivot that led to the multi-core processors we all have in our devices today.
This slide just captures the new philosophy perfectly. See, in the old single-core days, power was treated like it was basically a free resource, but cramming more transistors onto a chip, that was the expensive part. By the 2000s, that had completely flipped on its head. We could suddenly fit billions of transistors on a chip. They were essentially free, dirt cheap. But the power needed to run them all at top speed, that was now incredibly expensive because it generated that killer heat. Power became the new bottleneck.
Let's see how this new philosophy created a whole new approach. The old way, that instruction-level parallelism, was like having one hyper-caffeinated, super-efficient worker juggling a ton of small tasks really fast. The new way, thread-level parallelism, or TLP, which is what multi-core lets us do, is totally different. It's like having a whole team of workers. Now, each individual worker might not be any faster than that old solo superstar, but by dividing up a really big job among the whole team, they get it done much quicker.
But as anyone who's ever managed a team knows, you can't just give a team the same list of instructions you gave to your one-star employee and expect things to work out. This hardware revolution forced an equally massive revolution in how software gets designed. You couldn't just write a long to-do list anymore. You had to learn to think in parallel.
And at its heart, it really just comes down to these 3 steps. First, you got to break a big problem down into smaller, bite-sized chunks. Second, you hand out those chunks to your different processor cores. And third, and this is the really tricky part, you have to figure out a way for all those cores to communicate and sync up their work so you get one final correct answer at the end. So, why does any of this techie stuff matter to you? Well, because this shift from single-core to multi-core, this big embrace of parallelism, it's the reason our modern world is even possible. This isn't some abstract engineering concept. It is the engine powering the technology you depend on every single day.
Just take a look at this number. In medicine, where every single second counts, this shift is a game changer. A radiologist might have to scan through hundreds of images, looking for these tiny, almost invisible nodules that could be early-stage cancer. Well, thanks to the massive parallel processing power in modern AI, those systems can analyze the scans and flag suspicious spots 26% faster. That's not just the statistic, that's precious time saved, leading to earlier and more accurate diagnosis.
And if you thought that was impressive, it gets even more impactful. When you're trying to diagnose really complex neurological conditions from brain scans, accuracy is absolutely everything. Parallel computing has boosted the accuracy of those diagnoses by a staggering 44%. I mean, just think about what that really means. This isn't about making computers faster for the sake of it. It's about giving doctors better tools, which leads to life-changing outcomes for real people and their families.
And truly, the impact is just everywhere you look. From the AI that recommends your next movie, to the scientific simulations that are modeling climate change, to the complex financial models that run our economy, none of it, absolutely none of it, would be possible without this multi-core revolution. It's the reason the supercomputer in your pocket can juggle your navigation, your music, and your messages all at the same time without grinding to a halt.
So this brings us to one final fascinating question I want to leave you with. If you have a team of 10 workers, right, 10 processor cores, but you only get a job done twice as fast as one person could have done it alone, is that a good result? On the surface, it sounds pretty inefficient, doesn't it?
And that, right there, is the ultimate lesson from this whole multi-core revolution. The goal of computing has fundamentally changed. We're no longer just chasing raw, blistering speed at all costs. It's about efficiency. It's about intelligence. The real challenge today isn't just making our machines faster, it's about making them smarter in how they use the incredible parallel power we finally unlocked. And that, well, that's the puzzle that's going to define the entire future of technology.